Can I ask a question?
Sure.
Could you go back one or two slides? Yes, one after this one. Yes, so it's about the sixth point. How is this microscopic parameter independence falls in the Bohmian mechanics, and if this is really a problem? I mean, if this is really a desirable quality or not.
Okay, so here the primitive ontology, PO means the primitive ontology in region A. The primitive ontology in Bohmian mechanics means the particle trajectories, the world lines. Okay, now consider a situation where, okay, let me make a drawing. Okay, so let me make a new drawing. Let's say here is region A, and here is region B. Okay, and now we have some particle trajectory here in region A. Okay, and now let's say A and B are chosen in such a way that that this is the time foliation, or this is one of the surfaces of the time foliation. Here's another one, etc. Okay, good. So now the following happens. The velocity of particle one over here, let's say that was somewhere on the trajectory here, depends on the simultaneous position, simultaneous relative to these surfaces, of particle number two. But here, the position of particle number two may already have been influenced by external fields, say magnetic fields, in region B. Okay, so say Bob can choose between this field and that field, and depending on whether he have this field or that, whether he applies this field or that field, you get this trajectory or that trajectory. So on the surface, you have this position or that position for particle two, and since the velocity of particle one depends on it, you would have correspondingly this velocity or that velocity. So correspondingly, the particle would go over here or go in a different place. Okay, so that's why the microscopic parameter independence is violated. Let me show you the equation again. Okay, so here what you condition on, what you specify is, say, initial positions, the hidden variables, initial data for the particles, and fields in A. And now what this says here is that the distribution does not depend on the fields in B. There's no difference whether you specify the fields in B or not. And what I've just drawn, that that shows that in Bohmian mechanics it does depend on the fields in B. So that's why this condition falls in Bohmian mechanics. So this is kind of trying to pin down what is it in Bohmian mechanics that that happens kind of faster than light. Okay, yes, there is something there. It's the dependence of things over here on on particles over there, and in fact even on external fields over there. So even what Bob does, the fields he applies have effects on the trajectory. These effects are not visible to Alice because Alice just sees one bit. She sees just the outcome of her experiment. And from that, she cannot see whether the trajectory has been influenced by Bob, because there's a general theorem in Bohmian mechanics that you have no signaling. You can't send any messages faster than at the speed of light. Okay, so that's the situation.
Thank you.
Does that answer your question?
Yes, yes. Thank you.
Okay. Okay, then I will continue with my slides here. So I have a few more things to say about how Bohmian mechanics actually works in relativistic space-time. Let's say for the Dirac equation. So here's the Dirac equation, or here written in Hamiltonian form. And now the Bohmian equation of motion for a Dirac particle would be this. You have a curve x mu, that's the world line, depending on some parameter. You could use proper time as the parameter or any other parameter. So this derivative here, that would be the tangent vector to the world line of the particle. And actually, what's relevant is only the space-time direction of the tangent, not the length of the tangent vector. You can always make the length equal to 1 if you normalize your parameter correspondingly. And the direction of this tangent vector in 4 dimensions is this. You take the wave function at this point on the trajectory. You form psi bar gamma mu psi. That's the usual formula for the probability current. And that's a 4 vector that gives you the tangent vector of the world lines. So in other words, the world lines are the integral curves of the probability current 4 vector field J mu. And here is the same thing written in a kind of in a different way, parameterized by coordinate time. And here you have 3 space coordinates. So that would be the apparent velocity in one particular Lorentz frame. You would get this formula. You see how this fits with the general structure of Bohmian theories. And then you get out that psi squared is actually conserved in every Lorentz frame. And you get out that these world lines don't depend on the choice of the time foliation. You don't have to even mention a time foliation to do it for one particle. That's different if you do it for n particles. Okay, so here in blue, I've drawn the surfaces of the time foliation. Now for every sigma in F, that is for each of these surfaces, we have a wave function psi sigma on this surface. Let's say now the configuration space on that surface would be sigma to the n points on sigma, a configuration on sigma. And the wave function would be a function on the configuration space. Now the configuration, if you have world lines, such as these, the red ones, then the configuration on sigma means the point where the first world line intersects sigma, which is this point, and where the second world line intersects sigma, this is this point. Okay, so that's the configuration on sigma. And then the expression for the velocity of particle number k would involve the wave function on this configuration. So here is for n Dirac particles, here's the formula for what it actually looks like. You see here psi bar, psi, so it's quadratic in psi. You have these gamma matrices here in the middle, and the other indices, the indices that you have too much, they're contracted with the unit normal vector. So n mu of x is the unit normal vector to the surface sigma at the point x. So you use that to contract some of the indices. Okay, so I wrote down the equation so you get an impression of what the equations look like. So there are some equations with which you can do it. Here are the key facts about this model, this theory, Bohmian mechanics, based on a given foliation of space-time. You have equivariance. Suppose initial configuration is psi square distributed, then the configuration of crossing points of on the surface sigma is psi square distributed for every sigma that belongs to this foliation. Predictions of this theory are that the detected configuration is psi square distributed even on surfaces that don't belong to the foliation. You can derive as a theorem that you have no superluminal signaling. As a consequence of this fact that you have chi-square distribution on every space-like surface, it follows that the foliation is invisible. By this, I mean that experimental results reveal no information about which foliation the foliation is. So in your experimental results, although the trajectories depend on the foliation, so you would have to assume that in nature there is a fact about what the true foliation is. You can't see from your experimental data what the true foliation is. That's a consequence of the equations of motion. It's a theorem in this theory that there is a limitation to knowledge. From the observed data, you cannot infer what the foliation was. Although it may seem to go against the spirit of relativity, I take seriously the possibility that our world might have a time foliation. However, there do exist relativistic, realist theories of quantum mechanics that do not require a time foliation. In particular, a relativistic version of the GRW theory that I myself had the privilege to develop. This theory is somewhat more complicated and less natural than Bohmian mechanics, but I will explain it to you in a minute. The wave function there, the wave function psi sigma on the space-like hypersurface sigma is random and evolves according to a stochastic modification of the Schrödinger equation, as usual in GRW theories. Okay, so now let's talk about GRW theory in relativistic space-time. When you start thinking about collapse and relativity, everybody's first idea is it cannot work. If collapse is instantaneous, as it should be according to the rules of quantum mechanics, instantaneous as opposed to propagating at speed c, then it must violate relativity. That's what you think at first. But that's actually not correct. This problem can be avoided. And I guess Aharonov and Albert in 1981 were the first people to explain how that would work. You simply associate with every space-like hypersurface sigma a wave function psi sigma. So you have a Hilbert space H sigma that's associated with that surface. For example, it could be n particle Dirac wave functions on that surface. So this would be the one particle Hilbert space. This would be the n particle Hilbert space associated with surface sigma. Okay, then on every surface you have a certain wave function. And then you could say, okay, if the surface is in the future of a certain collapse event, then you have the collapsed wave function there. And if the surface is in the past of a collapse event, then you have the uncollapsed wave function there. Okay, so I will actually define how the theory can work, how a GRW theory can work in relativistic spacetime, and I will use the flash ontology. Recall the flash ontology. It says matter is just in world points, finitely many points. Okay, so here's how the relativistic GRW model can be set up. Let's consider a fixed number n of distinguishable particles. The model works also at curved spacetime, but here I will describe it in Minkowski spacetime. It works also for interacting particles, but here I will just describe it for non-interacting ones. That's partly because the most interesting case is how can you get along with non-locality? How can you make something relativistic and non-local? But for non-locality, you have these particle pairs. It's not about interaction between the two particles. They're two non-interacting particles. They're entangled but non-interacting. So that's the difficult case, the real step that you have to manage. Okay. This model works also with the matter density ontology, but I will describe it here with the flash ontology. Now you know that in GW theories, you have kind of ordinary unitary evolutions somehow interrupted by collapses. The unitary part of the evolution will be regarded as given. So for example, it could be free Dirac equation. And I will assume that with every space-like surface sigma, there is associated a Hilbert space H sigma, and that the unitary evolution is an operator from H sigma to H sigma prime. So that means if I have two surfaces, then I have a law for how to do the unitary evolution from this surface to that surface. I suppose that is given. You can give me any unitary evolution of this kind that you think is reasonable. Okay, now based on that, I will modify the time evolution in such a way that I get a stochastic time evolution, a relativistic GRW evolution. Okay, so here I'm defining the stochastic process, the relativistic GRW process, at first for one particle, and then on the next slide, I will do it for several particles. I regard as given an initial wave function, psi 0, on some three-dimensional surface sigma 0, say t equals 0, somewhere in the past. And I will use the Flash ontology. So I will define where the flashes occur. I will define the probability distribution of the flashes. Now, for my procedure, I need to be given one flash to start with as part of the initial data. I call that a seed flash, okay, x0, some point in space-time. Now I will randomly select the next flash in space-time. Here's how. Let's say this point is my x0. Then I will specify a probability distribution in the future of x. So just inside the future light cone, so the dashed lines here, that's the future light cone. The probability distribution is concentrated in the future light cone. I randomly select a waiting time with exponential distribution. Okay, also in the non-relativistic case, it was an exponential distribution. But now t is the proper time between x0 and x. So once I've chosen this random value of the waiting time, I know that the next flash must be somewhere on this hyperboloid, because that's the surface of all points whose proper time distance from x0 is equal to this value. Okay? If there are any questions, just interrupt me and ask. Now I will evolve my wave function unitarily from whichever initial surface to that surface, the hyperboloid. Okay, now on this hyperboloid, I will select a random point, x, with probability density given by psi sigma squared. Actually, not exactly psi sigma squared, but convolved with a Gaussian on sigma so here's the Gaussian function on a curved surface. So this is the space-like distance along the surface. So you take the distance along the surface squared, you divide by this constant sigma, the same sigma. It's not the Pauli matrix, it's the constant sigma of the GRW theory. Okay, so that's the collapse width. It's the width of the Gaussian in the GRW theory. 10 to the minus 7 meters was GRW's proposal for the value of sigma, a constant of nature. Okay, so this is the curved Gaussian on this hyperboloid with width sigma. Okay, so okay, you do the convolution with this, so that means you smear out over the psi square distribution with this Gaussian. That gives you the probability distribution on this hyperboloid. You choose a point on this hyperboloid according to this probability distribution, and then you repeat the story. So this was my seed flash, a given space-time point. This was my hyperboloid. I choose a random point, let's say this one here, on my hyperboloid. That's my next flash. Now I start from this flash. I consider the future light cone of this flash, and in there I choose a random waiting time. Now this time it's smaller than it was here, just a short waiting time. So I get a hyperboloid. That's the surface of all points in the future of this point at the same time-like distance. And then on this hyperboloid, I choose a random point with more or less psi squared distribution, and then I repeat the story. Okay, so I get a sequence of flashes. Here's my x0, x1, x2, x3, x4, x5, and so on. So this is how I do it. Okay, so I get a sequence of flashes, and I always collapse my wave function. You see, on this surface, I take my pre-collapse wave function psi sigma, I multiply it by the Gaussian centered at the point x. Oops. So here's my point x. So think of a Gaussian around this point. Okay, I multiply my wave function with this Gaussian, so I get a collapsed wave function. Then I use this wave function for the next step of the collapse. Okay, so this is a completely relativistic procedure. I've used light cones and hyperboloids. That is what you have. What is complete? These are the surfaces that are completely relativistic. No choice of space-like surfaces involved. Good. Now we have it for one particle. That means now it follows from the definition that I've just explained to you in using this drawing and in words. It follows from this definition that the joint distribution of the first n flashes is of the form of this form. It's in terms of the initial wave function, the probability distribution is quadratic in the initial wave function, and here you have some operator. Actually, so the family of all these operators, B is any subset of R4 to the n, so that's any event that you could have for these n flashes. And G1n is a positive operator valued measure of POVM or POVM on this space here. So this is always a positive operator, and it's additive in the set B. And now, of course, you can do that for any number of flashes. Let's do that for all flashes together. So the probability distribution in the single particle case is now given by this POVM. And for the many particle case, you do it using the product POVM, which is defined by this equation. When you have several POVMs, you can always form the product POVM. Whenever the set you're considering is a product, then also this operator will be a tensor product, but in general, it will not be. And in particular, if the psi is not an entangled wave function, then this probability distribution will not be a product. If a probability distribution is a product, that means things are independent. Probability being a product means independence. But since psi 0 is not a product, the whole expression on the right-hand side is not a product. So the flashes are not independent for different particles. They're correlated. Okay, we have defined the joint distribution of the flashes. The random wave function is defined as follows. If the flashes up to a certain surface are given, then the wave function on the surface is determined by the initial wave function by collapsing the wave function whenever your surface crosses a flash. Okay, let's say you have you start with this initial surface, you push it towards the future. Every time you cross a flash, you collapse the wave function. Then actually it turns out the resulting wave function on this final surface doesn't depend on how you chose the surfaces in between. So you can also define a random wave function for every space-like hypersurface. You can prove with no signaling theorem. You can easily check that the theory is actually non-local. That is, flashes over here and flashes over there, even if they occur at space-like separation. For example, for particle 1 and particle 2, they could occur at space-like separation. For a single particle, one was always in the future of the other, so they could not be space-like separated. But for two particles, they can be space-like separated. And then the joint distribution is not independent. The joint distribution is not a product. So as soon as you think that nature has decided about the space-time location of one flash, that influences the conditional distribution of the flash on the other side. But there's no fact about who influences whom. So there is an influence. The two are not independent, but there is no fact in nature about who influences whom, whether the influence went this way or that way. They're just two random events, and they're coupled in such a way that their joint distribution does not factorize. As soon as you know something about the random choice over here, that gives you information about the random choice over there. But nature doesn't have to make a choice about which one came first. Nature can just say, okay, I choose these two things in a correlated way. Okay, so that's basically how this theory manages to be independent of the choice of foliation. It's kind of fully relativistic. It's more relativistic than Bohmian mechanics. It's still non-local. So this theory, relativistic GRW with flash ontology, illustrates that a theory can be relativistic and non-local. Then I also have a few slides on quantum field theory, but let me skip that and leave some room for questions. Thank you very much for your attention.
Since you did not represent this quantum field theory part, so I have no idea about it. But I was thinking that is there extensions to quantum field theory? Like now what is present is status, that is like a field is a, people take field like a primitive ontology, what you say in that technical term, whatever it is. Mm-hmm. And then they quantize it, and then they like make a operator analysis or whatever. Then you can there is a procedure of writing wave function for one particle, kind of. So in this way, like take a ontology, a field as ontology, then you write, you quantize it, and then take write a wave function for one particle, and then put this into Bohmian mechanics, Bohmian equation.
Okay, so for these this Bell experiment that I discussed and the similar experiments, it suffices to consider just n particles. So I described it as just n particle Dirac wave functions. For quantum field theory, okay, so it's a field of active research to extend these theories, Bohmian mechanics and GRW, to quantum field theories, and there are basically two approaches. The field in Bohmian mechanics, to use a field ontology or a particle ontology. So field ontology would mean, instead of particles, you have actual field configurations. So you regard the wave function as a function on the infinite dimensional space of all field configurations. And then there's one point in this space that is the actual field configuration. And then that satisfies some equation of motion, maybe like this. So this is some simple model that has been proposed. So that would be one possibility. Another possibility would be to still have particles, but to include particle creation and annihilation. And well, let's say for some models, for simple cases, this has been worked out. There are equations for that. Okay, so some models have been set up, but well, quantum field theory is big, a big field with many open questions. So it's still ongoing research.